To solve beam problems, we need to write a force equation. We need to choose a convenient pivot point where an unknown acts on the system and write a torque equation. And then we're going to solve the torque equation for the missing variable and plug that into the force equation. And we'll do two more examples here. So let's find the reactions. We're going to write a force equation where the ups equal the downs. Now what we have are, we've assumed anyway, that the reaction at A and the reaction at B act upward, which we don't know for sure, but it seems reasonable. So we're going to have the ups equal the downs. So we have reaction at A up, reaction at B up, and 800 is up, counteracted by 1500 down and 2000 down. Now, if you consider just the downs, 2000 plus 1500, that's 3500. 3500 down. But we've got 800 up. So that's a net of 2700 down. That's where that 2700 came from. So now we need to pick a pivot point, preferably over an unknown force, and find all the torques of all the other forces with respect to that point. So reaction B, force times lever arm, which is 7, in the positive or counterclockwise sense, plus 800 times a lever arm of 5, again in the counterclockwise or positive sense. This 1500 Newton force is 2 meters away from the pivot point, and it would cause this beam to rotate clockwise, which is in the negative sense. That's why we have a negative sign here. The 2000 Newton force is how many meters away? 5, 7, 11. And that would also cause this beam to rotate clockwise, which is negative. Force times lever arm. And all that should add up to 0. Solve that for the reaction at B, and we get approximately 3000 newtons. Now we're going to plug that into the force equation right here, and when we do that, the reaction at A comes out to be negative 300, which simply means that the reaction at A doesn't act upwards. In other words, to keep this system in equilibrium, we need to actually grab the end here and hold down 300 newtons worth. So don't be afraid if you get a negative answer for a force. It just means that the way you thought the force acted, in this case upwards for reaction at A, it actually acts opposite to that. Now let's do one example with a distributed load. Here we have a beam supported at certain spots. We've got certain point loads that act. And now we have a distributed load. It says here the beam's weight acts as a uniformly distributed load of 75 newtons per meter along the entire beam. Find the support reactions A and B. So, to deal with the distributed load, we're going to concentrate the distributed load into a point load by taking 75 newtons for every meter times 14 meters of length. That's the total weight, 1050 newtons. It's almost as if this green distributed load, if you imagine this as an even layer of snow that's acting on this beam, and I started pushing all this snow into the middle, that snow would weigh, if the snow weighed 75 newtons for every meter 75 newtons, every meter 75 newtons. I've got 14 meters of that. That 1050 Newton force acts at the centroid of the distributed load, which is the center of the distributed load. So here comes all of that force acting right at the center of the distributed load. Not necessarily at the center of this span between the reactions, but the center of the distributed load, which would be exactly 7 meters from each end, because this is a 14-meter beam. So, what we've done is we've taken the distributed load and we've turned it into an equivalent point load that will allow us to calculate the exact same reactions at each support point. So, now we proceed just like we always have. The ups equal the downs. RA plus RB, both are acting upward. 510 plus 1050 plus 930 acting downward. That's negative 2490. Now we need to pick a pivot point. Let's pick above point A. The reaction at B times 8 meters minus 930 times 5 meters, because that acts in the clockwise sense. 1050 times a lever arm of 3, right? This 1050 Newton force acts 7 meters from the end. And if it's 4 meters from the left end to the pivot point, then it's another 3 to get us to the 7 meters. So the lever arm, the distance between the pivot point and the force is 3 meters. All of these lever arms down here, 8, 5, 3, they're all measured relative to that pivot point. And we've only got one other force, and that's the 510 Newton force, and the 510 Newton force would cause this beam to rotate counterclockwise. So I'm expecting positive. Look at that. And those torques, if this is in equilibrium, need to add up to 0. Solve that for the reaction at B. I trust you can do that. Plug that value in to the force equation, and you're done. Here we looked at 2 new beam problem cases. 1. We always have to assume a reaction force points in a certain direction. If we solve for a force and it comes out negative, it just means that the force acts in the opposite direction to what we had assumed. And 2, the effect of a uniformly distributed load, on the reactions anyway, is the same as if the entire distributed load acted as a point load at the centroid of the distributed load.